There's another comparison test that we can use that will help us sometimes when the direct comparison test doesn't work. So same idea, it's called the limit comparison test. So let's say this is the series that we have. And let's try to see what happens when we use the direct comparison test. So I see a p-series in there. Let's make this 1 over 2 to the n. And if you do that, what's going to happen is this is our inequality. So we're comparing it to a p-series that we know diverges. It doesn't matter that there's the 1/2 in the front. This is a p-series that diverges, and this is always smaller. So direct comparison test says if something diverges, anything bigger will diverge. It doesn't say if something diverges, anything smaller that will diverge as well. So the direct comparison test is actually inconclusive. It doesn't help us figure out what's happening to this series. So this is where the limit comparison test comes into play. And you're going to start the same way. You have to find a series to compare it to. And it doesn't matter if you compare it to 1 over 2n or 1 over n. That 2 makes no difference. It's still a p-series. So I'm just going to compare it to 1 over n. So this is a p-series that we know diverges. So what we're going to do is you take the limit of the original divided by what you're comparing to. And it actually doesn't matter if you flip it or not. So if I rewrite this, right, just rewrite it as a multiplication problem, gets multiplied by the reciprocal, so this becomes this, which is what I've up here. We're taking the limit as it goes to infinity, degrees are the same, ratio of the lead coefficient gives me 1/2. So when you do the limit comparison test, it says that if you get to a limit where what you get is any positive real number, then the series do the same thing. So because we compared it to a p-series that diverge, and I got to a limit that is a number, they are both going to diverge. Now notice, if you had compared to 2 over n, it's not going to change my conclusion. Your limit would be 1, but the conclusion would still be the same because you still got to a number. Okay. Let's try another example. And what you want to do is the limit comparison always works when you have basically a rational function where the top and the bottom are both polynomials, because you can always compare it to a p-series. So look at this one. Compare it to a p-series. You always want to compare the highest degree on the top, highest degree on the bottom. So we're going to compare to 1 over 3n squared. I'm going to say this is a p-series that converges. Limit comparison test says you take the limit of, and it doesn't matter which you divide by which. I'm going to go ahead and take the original divided by what you're comparing to, so we're going to flip it. So let's just make it into a multiplication problem. Your degree on the top and the bottom is the same. Ratio of the lead coefficient is 1. I get to a positive real number, so I can make the conclusion that the original series, they're going to do the same thing. So this converges by LCT. Okay. Same thing here. Let's try one more. Again, I see a polynomial on top, polynomial on the bottom. Look at the highest degree. So what you're going to compare it to is this. And it doesn't matter if you keep that 3 on the bottom or not. You can compare it to 1 over n squared. This is a p-series that converges. I'm going to do my limit comparison test. So limit of, we'll do the original divided by or multiply by what I'm comparing it to. Again, you should not multiply any of this out. What's always going to happen is you're just comparing degrees. Degree on the top and the bottom is the same, so ratio of the lead coefficient, so this limit is 1. So this is your work, and then you can also say this converges by LCT. So this is what you need to show. Show me the series that you're comparing it to, what happens to there. Show your work if you need to. This is just a p-series. Show me your limit, get to the correct limit, and then draw your conclusion on what's happening to the original.